Lesson 4 has 4 parts. The first part is on radian measure of angles, and let's just think about that. This should be a review for you. And if you had a circle, here's the center, and there's a radius for the circle. If you went around that circle one time, that would equal 360 degrees, and it would also equal in radians 2 pi radians. If you remember, radians is just another way of measuring an angle. 360 degrees is the same thing as 2 pi radians. So if we simplify that, divide by 2 on both sides, remember pi equals 3.14, that would be the rounded value for that. 180 degrees equals pi radians. We have these things are equal to each other, but they look different because their units are different, right? Just like 2.54 centimeters equals 1 inch. The numbers are different. That's because the units are different. We could use this as a unit multiplier. 180 degrees over pi radians, or pi radians over 180 degrees. Either way. The ratio equals 1, right? Because those are equal quantities in the numerator and denominator. If you've done physics, and also if you've done advanced mathematics, maybe you remember this formula. Velocity is equal to r times omega. That's the angular velocity for a rotating object. It's equal to the radius times that angular rotation rate, and omega has to be in radians per second. So if we were given a radius equal to 5 feet, that little tick mark means feet, and an angular rotation rate of 10 radians per second, we would multiply those two things together and get 50 feet per second. Now, what happened to the radians? Why isn't it 50 feet times radians per second? Well, when you do these problems, you just kind of make the radians units go away. You don't really worry about those. That's why you use the units of radians in a problem like this. You won't say revolutions per second or degrees per second. You need to make sure that the units are in radians per second. Let's go ahead and do a practice problem. This one says the wheel rotated at 30 RPM, or revolutions per minute. If the radius was 3 feet, how fast was the wheel moving? So think about what's happening here. We have this wheel with a radius of 3 feet. It's rotating at 30 revolutions per minute. So if the angular velocity of that wheel is equal to its radius times its rotation rate, that speed at the outside edge is equal to r omega. So that means the speed in the middle is also the same, or the speed of the wheel moving along. The speed of that wheel moving along on the ground, it's going to be as fast as that fastest point on the wheel. That's kind of strange to think about, but since that angular velocity is equal to the radius times the rotation rate, a point right here on the wheel is not moving as fast as a point on that outside edge because that radius distance is shorter. Think about it. Watch this circle right here. In one revolution, a particle would travel that distance. But if it's on the outside edge, it travels the circumference, which is a lot farther distant. So in order to do that in one revolution, it must be traveling faster, right? But anyway, the entire wheel moves at that fastest point, wherever that's touching the ground. So that would be at the outside edge. We need to solve for how fast it was moving. That would be velocity is equal to 3 feet. And we'll just do this in units of feet per minute. So 3 feet times omega of 30 revolutions in 1 minute. Now, we need radians and not revolutions. So there are 2 pi radians in 1 revolution. So there's another conversion factor. We didn't really talk about that before, but since there's 360 degrees in a revolution, there's 2 pi radians in a revolution as well. So the revolutions cancel, and we don't concern ourselves with the radians units. We can say 3 times 30 times 2 pi radians, or not radians, feet per minute. We don't worry about the radians anymore, so we take those out of the answer, and we just say, I'll just say FPM, feet per minute. This is usually how they want your answer. Obviously, we could multiply all those together. We'd have 180 times pi. Usually on these radian per minute problems or revolution problems, they'll want the answer just left as the factors. They want you to use conversion factors to solve these problems. So anytime usually in Saxon when you use conversion factors, they just want you to write the answer as the individual factors and then have the units right. As long as you have the factors and you have the units right at the end, then you can consider the problem correct. Let's go ahead and go to part B of this lesson on trig ratios, and this is something you've been doing since Algebra 2. You first learned it in Algebra 2. This deals with right triangles, and let's call this side A, this side B, and this side C. We'll call this angle right here theta, and let's put a little box right there on the corner so that we know that that is a right triangle there. And if you recall, trigonometric ratios, those are a way for us to compare similar right triangles and compare the ratios of the sides. In all similar triangles, the ratios of the sides are proportional to each other. That's where the value in having these ratios of sides of a right triangle comes into play, is because similar triangles, their sides are proportional to each other. So what we do, if you remember, we have sine and cosine and tangent. Sine, we just abbreviate it sin theta. What we're saying there is, for that angle theta right there, sine of theta is the ratio of the opposite side to angle theta, which would be side A, over the hypotenuse, which would be C. Sine of theta is equal to A over C. It's just a notation. Sin is notation. It's not like we're saying sine times theta or something like that. It's just sine of theta. It's functional notation. Theta is a function of A over C. Or sine of theta is a function of A over C. The value for sine theta depends on the value of A and C. And cosine theta, we just abbreviate that cos theta. That's equal to the adjacent side B over the hypotenuse. And then tangent theta, we just abbreviate that tan theta. That's equal to the ratio of the opposite to the adjacent, A over B. Recall that we also have reciprocal functions, cosecant, secant, and cotangent. All of these relationships that we're talking about here, these would be good to put in your spiral notebook. Hopefully you remember using, especially sine, cosine, and tangent, hopefully you remember those well enough from advanced mathematics that you already have those memorized. I have two 30, 60, 90 triangles drawn there. They're different sizes, but they're similar triangles because their angles are equal. Remember, that's how we define similar triangles. So that means the ratio of their sides is equal. And you can type sine of 30 degrees into your calculator and you should get 1/2 as the answer. I use a TI 83 Plus graphing calculator, and you'll want a graphing calculator for this course if you don't already have one. That's the one I also used in advanced mathematics. But if you type in sine of 30 on there and you don't get 1/2, it could mean that you are in radian mode instead of in degree mode. If you don't get sine of 30 equals 1/2 on your calculator, go to the mode button. It's at the top left of your buttons. Press that and scroll down 3. Use your arrows to go down, and the third row you'll see radian and degree. Degree should be highlighted in black. If it's not, go down until your cursor basically is over the degree symbol and degree is flashing, then hit enter. Go back and make sure sine of 30 does equal 1/2. And see, sine of 30 equals 1/2. It doesn't matter how big the triangle is, as long as it's 30, 60, 90, the opposite side to the hypotenuse, that ratio will always be the same. And that's a fundamental special triangle, we call them. This side is 1, this side is 2, and this side is the square root of 3 on a 30, 60, 90. Adjacent over hypotenuse is a square root of 3 over 2, or about 0.866. That's a triangle you'll want to memorize the ratio of the sides for, and the same thing with a 45, 45, 90. The sides there are 1, 1, and the square root of 2. So 45, 45, 90, we have two angles that are 45 degrees. If you have similar angles, the sides opposite them should be equal. And they are. This is a base triangle that we have here, just a basic standard one, with the sides equal to 1 in length, and then the hypotenuse is the square root of 2 when that happens. So it's good to know what the sine and cosine especially are for a 30, 60, 90, 45, 45, 90 triangle. Why don't we just go ahead and write down some angles here and the corresponding radian measures for them. Those would be good to know as well. So if we had 0 degrees and 30, 60, 45 degrees, 90 degrees, 180 degrees, 270 degrees. Those are some good ones to know the corresponding radian measures for. So for 0 degrees, we'd have 0 radians. For 30 degrees, that's pi over 6. You can just multiply 30 degrees by pi over 180 to convert from degrees to radians if you want to make sure that what I'm doing here is right. 60 degrees is pi over 3. 45 is pi over 4. 90 is pi over 2. 180 is pi. That should make sense because we've already said that's a conversion. 180 degrees equals pi radians. And then 270 would be 3 pi over 2. So these are obviously units of degrees on the left, and these are radians. Those are just some good radian values to know for corresponding degree measures. Let's go ahead and do a practice problem. Evaluate this relationship here. Sine squared of pi over 6 minus secant of 3 pi over 4. So what I like to do on these is just set up a Cartesian coordinate system underneath each one, and that just helps me get my bearings basically. So you think about sine squared of pi over 6, and remember that sine notation, that's just functional notation. You're not squaring sine, you're really squaring the value that you get for sine of pi over 6. You're squaring that value. Pi over 6 is 30 degrees, so that would be over here, and we would have an opposite side of 1 and a hypotenuse of 2. So sine of pi over 6 is 1/2, but we're going to square that value. And then secant, that's 1 over cosine. Let's just think about 3 pi over 4 for right now. We'd have pi over 4 would be about right here, then 2 pi over 4, then 3 pi over 4 is right there. So on that side we'd have basically 135 degrees is what that would equal to. Because pi over 4 is 45, 45 times 3 is 135, and that means we have an opposite side of 1 and adjacent side of -1 since we're to the left. And cosine is adjacent over hypotenuse. We have secant here, which is 1 over cosine, so we're looking at hypotenuse. Actually, this is minus, not plus. Hypotenuse is the square root of 2 over adjacent, which would be -1. Cosine is adjacent over hypotenuse. Secant is hypotenuse over adjacent. So let's just simplify here. And we'll have 1/2 squared would be 1/4 plus, not minus, we have a minus over minus there, plus the square root of 2. And we can just leave our answer like that. That should be okay. So you'll have other problems like that where they'll ask you to evaluate a particular function, and that's what you're doing. You're finding its value for those sine functions that have been given, or trig functions that have been given. Let's go on to part C on the 4-quadrant sines. Now, maybe you remember in advanced mathematics just how deductive the study of trigonometry was, when we started with those basic rules, the sine, cosine, and tangent, and when we learned all kinds of new truths based on that. Trigonometry was actually developed after Euclid's Elements. It was developed around 150 years before Christ. A man named Hipparchus was the one who's credited with developing trigonometry. They did not use a Cartesian coordinate system. That wasn't developed until much, much later by René Descartes. We use a Cartesian coordinate system to help us understand the different trig ratios and some of the results we'll get for these trig ratios. If we think about a Cartesian coordinate system and we think about the degrees in a circle, 90, 180, 270, 360, and then we remember also that all angle measures are started from that positive x-axis and we move up from there. What we can do if we want to find like the sine of an angle that's between 0 and 90, we can set up a little similar triangle in there that has a radius of 1. If we're thinking about a circle anyway, it'd have a radius of 1. And let's say this was a 30-degree angle that we were dealing with. If that was the case, then the opposite side would be 1/2, and this side would be the square root of 3 over 2. So in that range from 0 to 90, all of the adjacent sides would be positive. All the opposite sides would be positive as well. So that means sine, cosine, and tangent all would be positive in that first quadrant. Then just think about the second quadrant. You would have the adjacent side would be negative. So in terms of sine, cosine, and tangent, cosine and tangent have the adjacent side in them. They would both be negative. Sine, that's not sin, it's sine. Sine is positive in that second quadrant. Then the third quadrant, think about anything in that third quadrant. That opposite and adjacent would both be negative. So sine would be negative, cosine would be negative, but tangent would be positive because it's opposite over adjacent. So it'd be like a negative over a negative. Tangent is positive there. And then in the fourth quadrant, your opposite side would be negative. So tangent and sine would be negative. Cosine is the only thing that's positive. In the book they have a little memory aid to help you. All students take calculus. So you have like 4 words there: first, second, third, fourth quadrant. First quadrant, all. A is for all, R positive. And then the second word is students. The S stands for sine. Sine is positive in that second quadrant. The third word is take. The T is for tangent, and the third word is for third quadrant. So tangent is positive in the third. Calculus, the fourth word, that means the fourth quadrant. C is for cosine. Cosine is positive. Just a little memory aid there to help you with your different quadrants and what sine, cosine, and tangent values are, if they're positive or negative in those different quadrants. Let's go ahead and do another problem here. Let's add these two together. 4 cosine of 11 pi over 6 plus sine of 2 pi over 3. First thing I always like to do on these problems is just make a Cartesian coordinate system under each relationship and just think about that. I have a 4 as a coefficient or a factor in that first one, so I'll be saying 4 times cosine 11 pi over 6. And so I just think about that. 12 pi over 6 would be 2 pi radians, or 360 degrees around. So 11 pi over 6 would just be pi over 6 less than that, or in other words, 30 degrees. So I'm down there in that fourth quadrant. I remember that cosine is positive there, or I can just look at it too and see I have that adjacent side. And I'm dealing with basically an angle there of pi over 6, which equals 30 degrees. Cosine of 30 degrees is the square root of 3 over 2. So I'm doing 4 times the square root of 3 over 2. And those cancel, and I'm just basically left with 2 times the square root of 3. And then sine of 2 pi over 3, well, pi over 3, that would be 60 degrees. Then another 60 degrees would be 2 pi over 3. So basically from there to there, that's 120 degrees. That means this right here is 60. I know that writing's a little bit small, but hopefully that makes sense to you. 3 pi over 3 would be 180, right? We're doing multiples of 60 degrees. You always try to set up a triangle, a right triangle, relative to the x-axis. And so here we're doing sine. In that second quadrant, that's going to be positive, we know. Well, we just look at the opposite side too, and we can see it's positive. 60 degrees, that means that side is the square root of 3 over the hypotenuse of 2. So we'll be adding 2 times the square root of 3 plus the square root of 3 over 2 together. We could go ahead and get a common denominator here. Just multiply on the left by 2 over 2, and we'll end up with 4 times the square root of 3 plus the square root of 3, which would just be 5 times the square root of 3 over 2. That's the evaluation of that problem. Evaluating trig functions, it helps you basically with answering the question, where am I? You've got to always know, what quadrant am I in? What's happening with my special triangles that I can make? Is the opposite side positive? It's going to be negative. What's going to happen here? Hypotenuse is always positive. You're just looking at the opposite and the adjacent sides and their signs as to what your cosine, sine, and tangent sign will be. I wouldn't worry so much about memorizing that memory aid. All students take calculus to remember what trig functions are positive and what quadrants. The most important thing is knowing that you always set up your angle relative to the x-axis. If you can build a triangle off of that, then you can always tell what its sides are going to be, whether they'll be positive or negative. And then you can figure out what your sine, cosine, and tangent are from there. The last part of this lesson is on simplifying trig functions, and basically all you're doing here is trying to get down to maybe one, hopefully just one trig function from a set of trig functions, usually represented as factors of each other. So look at problem D here. Cosine squared theta times secant theta over sine of theta. what I usually do on problems like this is try to get them in terms of sine and cosine first. Break everything down just in terms of sine and cosine, and then you can build it back up, cancel things as you need to simplify. So let's go ahead and do that. Cosine squared theta, think about that. It's just notation. It's saying cosine of theta twice, or cosine theta squared. Secant theta is 1 over cosine, right? And so that means that one of these cosines will cancel. I can just remove that squared symbol, cancel that cosine, because we're saying cosine times cosine divided by cosine. So that's the numerator is now just cosine of theta over the denominator of sine theta. Well, sine over cosine is tangent. Cosine over sine is the reciprocal of that, which would just be cotangent theta. So we simplify that to just one trig function, cotangent theta. That's all you have to do when you see simplify problems like that. The best thing to do first is to remember just to break it up into sines and cosines first. Cancel where you can. Try to get just one trig function for the answer. All of these things we're learning right now are most of it, everything is stuff that you should have seen before. If you didn't, that means you probably didn't do Saxon Advanced Mathematics. Maybe you did something else. Get real familiar with those trig functions again. You'll be using those quite a bit in calculus. Okay, well that's all for lesson 4.